data. Michael is a data scientist at InfoChimps, so please give him a warm welcome.
So I work for a big data company, InfoChimps. We provide big data services, and I see a lot of news out there about big data is going to unlock an enormous value, billions of dollars, and I don't see a lot of news articles about why. So I thought I'd try to answer that and explain why it's not just hype. There is value in big data. Oops. There. So a little about me. I went to school at Georgia Tech, where I did computer science with a specialization in machine learning. I went back to school for economics, where I ended up specializing in econometrics, and I feel that turned me into a data scientist. With the addition of some management consulting, thus the tie, and I went to New York a little bit after to be a data scientist as a freelancer, and then I moved to Boston. So unfortunately the Bruins, I made the slides before, anyway. And now I'm with InfoChimps. And yeah, so we can discuss at Mead Hall later what we do. So before we talk about big data, why data? So this is going to be a little more interactive. So can somebody give me an answer for why we care about data as opposed to case studies? All right, come on, hands.
Why aren't case studies real data?
Why are not case studies data? That's a good question. So data meaning many observations as opposed to a few. We had a hand there?
Just low sample size?
Right. So, but why do we not like low sample size?
We'd like to generalize.
Right. It's generalization, but some people can generalize from case studies, right? That's valid science. You investigate very deeply. Avoid bias. That's a good one.
It's easy to fool yourself.
It is easy to fool yourself. And we heard this from Nell earlier about overfitting. And that's exactly the problem. It is too easy to fool yourself that the model, you've generalized accurately from small data, few observations, but what you really did is you fit to the randomness, you fit to the noise. And so we need more data. That's why we need data in the first place. So I'm not sure of the background, but just a review about why we want to be building models in the first place, why we care about data and why we care about building models. So we got data, some variables, A, B, and C. We use those to, as Nell said, often fit a line, build a generalization from the observations. And we do that so we can make a decision, pick the right action so that we make money. So what is big data? It's kind of a...
Not small data.
More than fits in your system, not small data. Some people say it's more than fits in Excel. I'm looking for three...
Velocity, volume, and variety.
Yeah, a lot of people like to say velocity, volume, and variety. IBM likes that. They like to add veracity. I'm not such a big fan of veracity. But so volume, meaning just more observations of the same type. So you're observing more stuff. We've got variety, meaning more data sources, more types of things that we may need to merge into a single type of data. We have velocity, data that's moving very fast or processed quickly, and veracity, accurate data. So we're going to use those things to solve some problems that small data or less data had. So what are some things that we'd want to fix problems that might arise from too little data? And we had some answers earlier about overfitting.
Sometimes when you have case studies, the data generated are basically based on people's subjective answers. With big data, which could be machine sensor data, it's very hard to lie.
Right, so it's harder to lie when you have a lot more data. It's less subjective, so that sounds like a bias, which is one of the words I was looking for. And variance. Exactly, so those are the two ways you can go wrong with bias and variance. Other fields might call it precision and accuracy. So these are the two things that ways your model can be wrong. Either you can be biased if you've been, say, only asking one person, or you can have too much variance if there's a whole lot of noise in your data. So when you draw your line through really noisy data and you're guessing, all of your predictions are on that line, then your variation in the error, your prediction error is going to be all over the place. Right, the actual points are way up and down off the line, and that's variance. And then bias is if you drew your line like to the side. Even if all the points were really tightly clustered, and your predictions have a very consistent error, if you're just off by the same amount all the time, that's your bias. And you can have obviously both bias and variance, and this is one of the central trade-offs actually in machine learning and statistics is, do you pick an algorithm that gives you bias or one that gives you variance? And there's a no free lunch theorem. It's a lot of fun, and that means you can't get both. You can't get low bias and low variance. You have to choose. And that comes into picking your error metric. We had a question earlier about how do I pick the right error metric. It's that's that balance that you're going into, is whether you care about bias or variance. So this one's already been hit on with noise. You know, why might we have variance? And the metaphor is signal to noise, right? So if we this is an image of white noise. If we have a low signal to noise ratio, then the solution is to increase the volume of your data. And that metaphor of, say, volume in terms of like a megaphone, that's not quite the same metaphor. It's because if you're, say, if all the crowd is speaking, and I'm trying to, and I switch to a microphone to speak over the crowd, then that's increasing the signal to the noise. That's not what we're talking about. We're not talking about changing the ratio of signal to noise. We're talking about looking at the same type of information, just more observations of it. And statistics and machine learning are really good at using that more observations to narrow in on the signal, even though there's a huge amount of noise. So why might we have bias other than so we already touched on selection bias, or asking too few people. Yeah.
You might want something simple, so you want a simple model rather than a very complex model. So you want a bias or a model to have this only we want to use only one term or two terms or three with one things rather than all the information. So you want a very simple model.
Right. A simpler model would, in many cases, reduce the bias at the cost of variance. But I'm looking for why would your data cause you, why would your predictions have bias other than selection bias in terms of asking the wrong person? Yeah.
How do you do the measurement bias?
Yeah, measurement error. That's a great one. That ties into veracity. Yeah.
Not training on the same data set as testing, which happens quite often if the data changes in time.
Yeah, changing in time. So that was not testing on the same data as training. So this is a term called non-stationarity, so when your data changes over time, it's very similar to selection bias in asking only taking a survey of say Boston Python people instead of just the average population. If you were to take a survey, or if you wanted to predict where the sun is going to rise tomorrow, and you've got maybe Copernicus's data from I forget when, and you've got like a huge amount of observations, that's going to be great data. You know, you could predict with incredible accuracy sort of these astronomical events. But if you want to predict what's the weather going to be like tomorrow, you need data from today. Like, I don't care what the weather was like 100 years ago because it's going to be off by like a few degrees anyway, sadly. So I thought I'd throw in a cartoon about sample bias. You know, if you just ask the wrong people, that creates sample bias. And I didn't put in a graphic about non-stationarity, but that's say looking at the stock market or the weather. There's a great deal of movement over time, and you just need recent information. And so these aspects of bias and variance, noise, selection bias, non-stationarity, and measurement error, are what you can overcome with the various aspects of big data. You've got a lot of noise, increase the volume. You've got a selection bias, look for more data sources, get greater variety. If you've got non-stationarity, quickly changing data, then get more recent data, get higher velocity data. If you've got measurement error, well, I like to cross that one off because it's really just a variety problem, right? If you've got somebody who's giving you bad measurements, go get another data source, get more variety. And so I also promised in the blurb for the talk how to do machine learning even if you're not an expert. So we have some great demonstration of scikit-learn, right? Machine learning is easy. You just use scikit-learn. So if that's easy, then why is it so hard? We also had a little bit of that discussion, which is data is hard. Getting the right data. Scikit-learn needs a matrix, right? If your data is coming in as blog posts and the weather, right? That's got to get turned into a matrix. You got to get weather balloons out there. You've got to transform your blog posts by some counting words into some form that these mathematical structures can accept, and that's hard. It is figuring out what to measure. Measuring all aspects of it, because I could take a survey of the room, that's pretty easy, but taking a survey of a non-biased survey of the United States, that's hard. And measuring recent events, you know, sometimes it's easy to, if you want information on, say, if you're a business and you want your sales, you can, you know, go ask you can watch things as they leave the warehouse. That data is pretty good. Your warehouse is being tracked. But if you want to track orders as they're being written down, say if you're a mail order catalog, and it's kind of an older example, but how would you know when somebody's writing down their order and is about to mail it to you? You know, so it can be hard to measure recent things, get a good non-biased sample, and actually measure what matters. And I wanted to. So a lot of people like to define what data science is, so I try different ones. So don't quote me on this one. But data science, you could say it's the art of estimating what is hard to measure using things that are easy to measure. So we can go out and, you know, it's hard to measure, and in some ways impossible to measure, something like somebody's propensity to buy. Right? If we want to know what's the likelihood that somebody's going to buy my product tomorrow, that's this really ephemeral quality. And the way we use data we can measure, use things we can measure to estimate that sort of concept of likelihood to buy. And that's what it's all about. It's figuring out the right, picking the right measure of error, like how much do I care if I'm wrong, or in what way do I care that I'm wrong? Is it a Price is Right style error, or is it absolute value error, or is it worse if I'm way off than if I'm a little off? So you may do squared error. Things like that when you pick, so picking what to measure, picking how to measure when you're wrong, how to measure what even to you're trying to optimize. Am I trying to optimize profit or revenue or things like that? That's what's hard. And if you are able to pick good measurements, then you don't have to worry as much about the machine learning part because you've already won. And so I will turn it over to questions. We got 5 minutes, I think.
Yeah, great.
All right. Yeah.
So when you say we want a large volume of data, can you measure this? Is it so I can have 50 samples? Or would you be having with 100, 10,000?
Good question. So the question was, how do I know when I have enough data? And so this is, if you're thinking about statistical significance. So statistical significance is somewhat arbitrary. You say it's a measure of whether your analysis is trustable or not, and you could say you can statistically analyze how confident you are that your analysis is correct, and you could do a power test. So there's a mathematical way to figure out if I want to detect this sensitivity of relationship, right? So if you want to look for things that will increase your profit, and you only care about things that increase your profit by a certain amount, like 1%, and you don't care if it's going to be less than that, then you can design a test to only detect things. You only need enough observations to detect a 1% change or a 1% effect. Then so the amount of data that you need is relative to the size of the effect that you want to detect. If you want to detect something very small, right, a low signal to noise ratio, then you need way more data than if you want to detect something that's a really strong signal. Good? All right. Yeah.
So you mentioned that big data helps you deal with this issue of having, say, a bias or not having
Yeah.
variety in your data. So how do you know? It seems like just having more data doesn't by itself correct that problem. So
Right.
how do you know that you're not just getting more of the same? You're getting
Okay.
a wider range?
That's a good question.
Repeat the question.
So how do you know when you have removed bias? If you're getting a good sample that is across the entire population instead of only a subgroup that has a particular bias. So if I wanted to measure where does the average Boston Python person live, if I measured where I go home every day, that would be I could know very accurately where I live within just a few observations, but that would be a terrible model of where a Boston Python person lives, right? So I could try to take a sample of the left half of the room and follow everybody there, but maybe the people on the right half of the room are all from the same neighborhood. And so unfortunately, it's intuition, and you have to know, you have to have a sense of what is a plausible correlation between how you've created your sample and the thing you're trying to predict. So if it is plausible that the side of the room you're on is related to where you live, then you should change the way you observe. You get data in relationship to that. If it is not plausible, if you're saying, okay, who cares? That's just not going to matter. Even if it does matter, it's probably overfitting. It's probably just noise. Then that's fine. It comes down to the story you tell and whether somebody believes you. Yeah.
Last question. So a lot of these examples, you have the idea that you have something that you want to discover, like profit or something, and you now talk about how do you go about collecting the data, measuring the data. But a lot of my impression is a lot of data science it goes the other way. They say we have all this data, we have a company with lots of log data. It's not necessarily design in any particular way. It's not design. You can't go off and measure what you want, decide what you think is most important data, and go find something interesting from that.
So,
rather than the other way you talked about, which is going from something hard, it's really hard question you want to learn, and come to figure out how do I.
Yeah, that's an excellent question. It is so most of the time you have data before you have a question, and even though it'd be great if you could come up with your question first and then go find the data, that's just not how it works. And I mean, this is a classic problem with science in general, is you should be forming your hypothesis before you collect data so that you can have you can design your data collection method with your question in mind, so that you avoid these problems. Physics, you can do your experiments, but with social sciences and businesses in general, you have to rely on natural experiments, things that have already happened, and you go back and figure out how to change that into some semblance of a controlled experiment. So all I can say there is that you just go through this process of look at what data you have, graph it, do a lot of exploratory visualization, figure out what questions sound interesting, then go back and look at your sampling method and make sure that you try to remove bias. And it's this cycle of exploration, analysis, and back and forth. And that's how it gets done. Yeah.
All right.